Hello everyone, this is going to be the video about the definition of the cross product in three-dimensional space. The purpose of this video is to give you the motivation of the definition of the cross product. So I assume that you're already familiar with the algebraic definition of the cross product. But first let's review the definition. So if A is a vector with component a1, a2, a3, and B is a vector component b1, b2, b3, the cross product of A and B is defined to be this vector here, where I and j and k are the standard basis vector. So I is 1, 0, 0, j is a 0, 1, 0, and k is a 0, 0, 1. And these are the determinant of the 2 by 2 matrix. And what this definition does is it creates a vector that is perpendicular to the vector A and B. So what we are actually going to do here is that we're going to translate this perpendicular condition to a linear equation, and by the process of solving the linear equation, we will observe that this type of formula shows up naturally. So let's write that down. The condition that vector A is perpendicular to a vector with component x, y, and z will be this condition right here. a1x plus a2y plus a3z equals 0. So that is this is the left-hand side of this equation is the dot product of vector A and the vector with component x, y, z. The second one will be the perpendicular condition in terms of dot product for the vector B. So the one way to solve this linear equation is the Gauss elimination method, and here the coefficient is unknown, so if you do the Gauss elimination method, the coefficient will be quite bulky. So we will use the following trick. We're going to insert actually an equation so that it makes this 3 by 3 coefficient matrix. Then we can use something called Cramer's rule. Because this is happening in this three-dimensional space, we know there exists a vector that is perpendicular to given vector A and B if A and B are not parallel or completely opposite to each other, or they are completely the zero vectors. So let this C1 and C2, C3 be the vector that is perpendicular to A1 and A2, A3, and insert the equation like this and pretend this is another unknown, another condition we're posing. So x, y, z is actually can be C1 and C2 and C3. So the first condition look like C1 squared, C2 squared, and C3 squared. But if you turn that into an equation like this equation becomes a 3 by 3. It has a 3 by 3 coefficient matrix. And because we know the solution exists, and we know that k is going to be non-zero, in particular it can be positive. So this system of linear equation will always have a solution as long as this k is a non-zero. So because it has this square matrix size, we can use something called the Cramer's rule. Cramer's rule gives a straightforward algebraic solution to the system of linear equations. So x here is the first component of the unknown vector x, y, z, and the Cramer's rule gives the following formula. 1 over the determinant of m, where the m here is the coefficient matrix of this system of linear equation, multiplied by the determinant of this 3 by 3 matrix, which is almost the same as m, except this first column is replaced by this column across this equal symbol of this system of linear equation, k 0, 0. Well, that's what the Cramer's rule says. Let's apply this to the second component of the vector x, y, z. Then it says the following. Y has a similar shape it has 1 over the determinant of m is the same as before, multiplied by this determinant where this middle column is replaced by k00. It's the same k00 we had before, but it replaced the second column because the y you see here is the second component of the unknown vector xyz. And here's the z part. That is exactly the same, and the same pattern that this k00 appeared in the third column because z is the third component of the vector. I think this pretty much answered our questions, because x and y and z has this common factor of 1 over determinant of m, 1 over determinant of m here, and there's 1 over determinant of m. Moreover, if you apply this cofactor expansion to this determinant of 3 by 3 matrix, this only picks up the following term, k times the determinant of this 2 by 2 matrix right there. Because this first column has this 0, 0, all the other terms in the cofactor expansion turned out to be 0. So it has a factor of k out there, and divided by determinant of m times the determinant of this 2 by 2 matrix that happened to appear in our formula of the cross product. Same thing here for the y part. We have 1 over determinant of m, and because there is a 0, 0 column in the second column here, the cofactor expansion only picks up the non-zero, only non-zero term in the cofactor expansion is a k times the determinant of these 2 by 2 matrix that are non-zero here. So that's exactly this term in the definition of the cross product. And the same for the z component here. So because the third column has this 0, 0 entry, the only non-zero term in the cofactor expansion is this k times the 2 by 2 matrix that you see over here, and that's what you see in the definition of the cross product. So these x and y and z, they have the common factor of k divided by the determinant of m. So if we clear that common factor, and we can clearly see that after we clear that common factor, the vector xyz becomes this vector we have defined above. Let me also go over this slightly different way of looking at the problem. It's more straightforward proof. So here's the definition of the cross product again, and we're going to write that cross product with components x and y and z. And let me remind you again on how we calculate the determinant of 3 by 3 matrix. This method is called cofactor expansion. What you see here is a cofactor expansion of the first row. So the C is the first row, and its component is C1 and C2 and C3. And what you do with this first row is actually we calculate this determinant of 2 by 2 matrix up there, and determinant of this 2 by 2 matrix up there, and so on, and they are now just denoted by x, y, z. So that cofactor expansion will be simply just the sum of the product. Whenever you have the sum of the product, you can write it as a dot product of two vectors. So the C1, C2, C3 makes the vector C, and the other component, x, y, z, makes the vector x, y, z, which is the cross product. So this determinant is equal to the C dot with the cross product A and B. In our textbook, this product is called a triple product. So with this analysis, the proving the perpendicularity gets really simple. Let that first row C to be the vector A, so that this 3 by 3 matrix has the first row and the second row exactly the same. The skew symmetric property of the determinant map makes the determinant 0 if there is the same row. Therefore, the determinant of m here is going to be 0, that makes this dot product to be 0. Whenever we have a dot product to 0, we know these two vectors A and A cross B are perpendicular to each other. So that proves the property of the cross product, namely that it is perpendicular to one of the factors involved in their cross product. Likewise, if we set the second row, the first row to be the last vector there, B, then because the first row there and the second row there is exactly the same, therefore this determinant will be again 0. And that makes this dot product 0, and we know the vector B and the cross product is perpendicular to each other because the dot product is 0. So that makes a straightforward proof of the statement that A cross B is perpendicular to the vector A and perpendicular to the vector B. Although this is a quite straightforward proof, it's less motivational. It kind of uses all the result here, but this is general enough. So if one think about finding a vector with this perpendicular product, a perpendicular property in 4-dimensional space, then this technique still works. What we have to do is that we put those 3 vectors given. We require 3 vectors to determine one vector that are perpendicular to all the 3 vectors up to scalar multiple. So we will have 3 rows here, and extra row there, and play the game with the first row. So that will be a 4x4 matrix. And if we just extend this idea, it will be just another straightforward calculation to come up with a formula of a vector that is perpendicular to a given 3 vector in 4-dimensional space. So although this is straightforward proof, it has a very good generalization to a higher dimensional situation. So thanks for watching the video.